What we aim to do in this lesson here is to represent functions as power series. Power series is what we defined in the last lesson as, well, we kind of thought of them as an infinitely long polynomial. What we wanted to know then was what was the domain of that polynomial? And we called that thing the interval of convergence. How did we find that interval of convergence? We used the ratio test. In this lesson, though, we want to represent functions as power series through algebraic manipulation, through differentiation, or integration on some kind of known series. Why would we do that? Well, remember that sort of an overall goal for this whole entire unit is to take a function that's hard to work with. Maybe it is a transcendental function like e to the x, natural log of x, sine, cosine, tangent, and then turn it into something that's easier to work with. Remember, we started with Taylor polynomials, and this is the same kind of thing, but it just keeps on going and keeps on going as a power series. So we'll start with a warm-up question. This one will probably look familiar. Find the interval of convergence for the summation from n equals 0 to infinity of x to the nth. So we saw this warm-up exercise in the last lesson, and we were able to find it by treating this thing as if it was geometric. If it was geometric, we're thinking of the x as the common ratio, and that common ratio needs to be, well, the absolute value of it needs to be less than 1. And that 1 that's right there is the radius of convergence, right? And then we can take that x value, get rid of the absolute value by sandwiching it in between a positive and a negative 1. Again, that 1 there is the radius of convergence, and the negative 1 to a positive 1, we can think of it as the domain of this. It's a set of all x values that whenever we stick them into this summation, it converges to some nice finite number. We call it the interval of convergence. Okay, now then, in warm-up exercise 2, again treating this summation here as a geometric series, we want to find the sum of that series in terms of x. Since we're thinking of it geometrically, don't we have a formula which will allow us to calculate the sum of a geometric series? I think we do, and it goes a little something like this. S is equal to A, that's your first term, over 1 minus R, which is the common ratio. So we have to find two things here. We need our A value, our first term, and we're supposed to start at 0, so if I plug in here 0, no, not in here, a 0. If I plug in 0 here, this would be x to the 0 power, which is equal to 1, even if we plug in a 0 for the x. Now, ordinarily, that would be undefined. It'd be an indeterminate form, and you'd have to use L'Hopital's rule in order to figure out what it is. But for the purposes of power series and series in general, 0 to the 0 power is taken to be 1. All right then, now we also need our common ratio. And if we're treating this as geometric, the common ratio is just x. R is equal to x, which brings us then to the sum of the series. It is, A is 1 over 1 minus x. Well, there you go. So in other words, here, let me make some connections for you. We're defining this as a function. F of x is equal to the summation from n equals 0 to infinity x to the nth. And what we just discovered is that it sums to, right? This is an infinite series. Well, what does it sum to? For every value of x, it sums to 1 over 1 minus x. Isn't this just like an algebraic function? This is a rational function, something that you learned to graph back in Algebra 2 and probably perfected in pre-cal with some asymptotes and all of that stuff, right? So, a couple things. We just said that the interval of convergence for this was from -1 to 1. What that means is that any number inside here, whenever I stick it in for x, it has a finite sum. The power series converges. Anything outside of that, it would diverge, go off to infinity or something like that, or negative infinity possibly, or maybe even just oscillate, whatever. But anything that's in here, the sum of those terms is just equal to 1 over 1 minus x. Okay, so for example, 1/2 is in there. 1/2 is in there. If I were to plug in f of 1/2, that's equal to 1 over 1 minus 1/2, 1 over 1 minus a half, which is equal to 2, right? And you plot this thing as an ordered pair, 1/2, comma 2. If you were to graph all of those values, it would overlap the graph of 1 over 1 minus x. Here, let's graph that thing, shall we? We need an asymptote. Hey, where is the asymptote? So the asymptote here is 1 minus x is equal to 0. Add the x over, it's equal to 1. Joop, 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 joop. I'm going to say it's about right there. All right. And then as far as graphing the rest of it goes, maybe an x-intercept. Oh, we don't have any x-intercepts. We've got a 1 on the bottom. Doesn't matter what. 1 on the top doesn't matter what the bottom is. It's not going to ever cross the x-axis. So you actually have another asymptote here. Horizontal one. And how about a y-intercept? If we were to plug in a 0 right here for x, it'd just be 1 over 1, which is 1. I'm going to say that that's about right there. And then whenever I go to graph this thing, here's a portion of the graph, and then here's the other branch of it. All right, that is the graph of the function f of x is equal to 1 over 1 minus x, the rational function that you're so used to, and its domain, of course, is all real numbers except for 1. So x is not equal to 1. Okay. However, the power series, which converges to 1 over 1 minus x, it's not this whole entire picture. No. If I go right here to a -1, it starts here at -1, but there's an open circle on it, of course. And I only get this part of the graph here. Let's maybe make this one right. So our power series here, if I think of it as a function with its interval of convergence of -1 to 1, is called an interval of convergence because it converges to the graph of, or the function, 1 over 1 minus x, but specifically only over the domain from -1 to 1. That's what our lesson is all about here today. All right, here's all of this animated Pixar quality. Oh, did you want to watch that again? Okay, you get to. All right, there we go. We're going to be able to represent a function as a power series through algebraic manipulation, differentiation, or integration. We actually didn't do that in the warm-up exercise. We did the reverse of that. We had a power series and we represented that as a function. Now what we want to be able to do is work that kind of process backwards. I start with a function. What would it be as a power series? All right, so this first part of this is just summarizing in a nice, neat fashion what we discovered there on the warm-up exercise. If we define a function f of x as the summation from n equals 0 to infinity of x to the nth power, its domain is going to be from -1 to 1. All of those numbers that are inside here, inside that domain, those are numbers for which this series converges. And what does it converge to? It converges to some finite value, which is the output of this as a function, right? Input is anything that's inside here, the numbers for which this series converge, and the output is the sum, the infinite sum at that x value. All right, so here is that series, and then if you expand this thing out, again, it just looks like an infinite polynomial, and then we just discovered that that is equal to 1 over 1 minus x, but specifically for -1 is less than x, which is less than 1, right? Because that's the domain or the interval of convergence for this thing. Here is the graph of, as we saw it, this is almost as good as the graph I drew by hand of f of x is equal to 1 over 1 minus x, the domain being all real numbers except for x is equal to 1, where we have our asymptote. However, that is not the same thing exactly as our power series, because our power series has a smaller domain. It's a subset of that, and it's only this part of the left-handed branch, right? That's what it converges to. And again, that's why we call this thing this interval of convergence. Also, we're thinking of it as, hey, these are the values for which our power series converges to some finite number. All right, so in the next part of the lesson, what we will do is actually start with a function and then try to turn that thing into a power series.